Hey guys, I wanted to give you an introduction to our last unit that we'll be doing in chemistry, which is about acids and bases. I would have liked to have gotten a lot farther in this unit because it's probably one of the most important things to take with you to a college chemistry class, although it kind of builds on all the other things. Like you couldn't talk about acids and bases before doing solutions. What I want to do is talk to you about a few of the things that I think are the most important to take with you, and we'll have a little online activity at the end of the week to do, which I think is in the past has been really revealing to a lot of students about some of the things about the nature of acids and bases. I wanted to talk about a few of the properties today and a couple of what we call the definitions of them, which are kind of like how they work. Let me tell you basically what an acid and base is, and then we'll kind of get into how they work real quick. Acids, we can kind of think of some properties of acids. People think of acids just as, it's got to be harmful, it's got to be really corrosive. Some acids are corrosive, but actually, a lot of acids are in foods. As a matter of fact, most foods are acidic. If they weren't acidic, you probably wouldn't want to taste them. If something is really acidic, it's probably has a sour taste. I just bought some Sour Patch Kids, and those are very acidic. That's what gives them the sour taste. Um, Generally, acids feel sticky when they dry. Citric acid, especially, is one that does this. Um, strong acids, actually strong bases too, tend to have a strong smell, so they're volatile. They give off vapors. Um, Acids tend to dissolve metals and carbonates. If you have a marble countertop, you don't want to pour lemon juice on it because that'll dissolve the marble. Carbonates are the mineral in marble. And acids can be good conductors. That's why we have acid in batteries. So your car battery is full of lead and sulfuric acid is what makes that run. So that's why it's so heavy, because it's lead. But you never want to have one explode because you'll get sulfuric acid all over you, and it'll be a bad chemical burn. Um, Three of the most common acids we talk about: hydrochloric acid, HCl, nitric acid, HNO3, and sulfuric acid, H2SO4. But you see that these just look like ionic compounds with an H. H and chloride, H and nitrate, H and sulfate. Well, there's a reason for that. Um, Other things about bases. So if acids are sticky, bases are slippery. You can think about soap as being slippery. If you have base on your hands, it tends to feel like your hands never really get clean. They're always slick. That's kind of a slippery feeling. Um, Bases tend to taste bitter. Bitter foods uh, have kind of an astringent taste to them, very bitter. Most household cleaners are basic, with the exception of toilet bowl cleaner, is an acid. But bleach, drain cleaner, Windex, oven cleaner, these things are all bases. And so bases generally actually are not edible. So we think about as acid being bad and base being good, but you wouldn't want to eat many bases. Okay, most bases are salts that are dissolved in water. If you've ever spilled bleach and then let it dry out, or OxyClean and let it dry out, it's actually like a white powder that's left behind. Most bases are ionic compounds that are dissolved in water. Um, what makes an acid, and what makes a base a base? Um, there's some conflicting views on this. Um, but this is where we get into definitions. What chemically is happening? So I just talked a second ago about power of hydrogen as being the pH scale. The hydrogen is sort of the active part. No matter how you look at it, hydrogen is sort of the active part of any acid. That's why even when we name acids, we usually don't even say hydrogen acid. Usually we just say the name of the ion that goes with it, because most acids have hydrogen in them in some way. And so really what we're talking about with hydrogen is what makes an acid acidic. Now it just depends on how you look at it. Um, so generally when we talk about acids, we don't have the word hydrogen. So if I had a chloride as a minus ion and I put it with H, so if I had a hydrogen ion with Cl, I would get HCl, right? That's hydrochloric acid. Okay, so it's acid because of the hydrogen ion. If I had H in nitrate, I wouldn't call it hydrogen nitrate. I would call it HNO3. I would call nitric acid. Okay, so it's the hydrogen that makes it acid. Okay, so this was actually the very first definition of an acid. This is what we call the Arrhenius definition of an acid. And so when acid chemistry was first begun to be looked at a little bit more closely, people began to realize that, hey, acids tend to have these hydrogen ions. Hydrogen's got to be part of the formula. So this guy named Svante Arrhenius was a Swedish chemist, worked a lot with energy and different reaction rates and things like that. He sort of gave this definition that all acids, like hydrochloric acid, have to dissolve into a positive hydrogen ion and some other negative ion. Okay, which kind of goes along with what we did in the last chapter. Okay, and then he also said, well, bases are the opposite of that. Bases are going to give off a different ion, which is present in a lot of basic solutions. He said bases, a good example of a base is NaOH. So he says, oh, bases are just ionic compounds that are going to have some positive metal ion and then an OH ion, hydroxide. So this is going to be sort of the other part of the acid, or the other part of the base. So he says bases have to have hydroxide as part of their formula, acids have to have hydrogen. You'll notice that if I was to pair up hydrogen and hydroxide, what that would be. Give you a second to think about this. Hydrogen and hydroxide would make HOH or H2O. So essentially, these are the two halves of a water molecule. Hydrogen being the positive part and hydroxide being the negative part. And this is sort of a major, it seems really like an elegant solution, right? Like hydroxide and hydrogen, these are the two halves of acids and bases. And so you could come up with, when we dissolve hydrochloric acid, we get the hydrogen ion. And so we always get H plus with this. And with bases, we get the hydroxide as the negative ion with this one. Those are the two examples I just wrote out there. But there's a major problem with this definition, and that's that not all chemicals that are bases even have a hydroxide ion. And not all chemicals that are acids, well, most of them do, but there are a few chemicals that don't have an H. So it doesn't work for every single chemical. Good examples would be ammonia. NH3 is a pretty strong base, but there's no hydroxide in it. Okay, so according to Arrhenius, it has to have a hydroxide to be a base. Another one would be baking soda. Baking soda doesn't have a hydroxide. So how are these things behaving like bases in all their physical properties, but they don't have OH? So we have to adjust the definition. And this is where we come up with one that came out slightly, or just a few years later, which is the Brindstad-Lowry definition. So I shouldn't say a few years later. This was like 40 years later, I think this came out. A Brindstad-Lowry definition takes the important part about hydrogen and leaves it there. Acids donate hydrogen ions. Okay, that part we're keeping. But they have to donate it to something else. They donate the hydrogen ion to a base. Bases don't have to be OH. They can be anything that takes up a hydrogen plus ion. So hydroxide is one example of that, but there are lots of different chemicals that will take up a hydrogen ion. Okay, so let's look at this a little bit closer. By the way, my gosh, doesn't this guy have a scary face? I comment on this every year, but like, couldn't you smile a little bit? So acids are chemicals we said has to donate the hydrogen ion to something else. So we can remember from our last unit about solutions that positives and negatives always separate when we dissolve, but in the case of acids, they always donate the hydrogen ion to something else. So they'll donate it to whatever they're with. So it could even be water. Water could act like a base here. So if I mix hydrochloric acid with water, I end up, the acid wants to donate the hydrogen. Remember, it's an acid. That's what acids do. It donates it. And then I get this thing called H3O. H3O plus. H3O plus is what we call hydronium. And this is actually, hydronium is actually what you detect in an acidic solution, that this is what you sense as acidic. Okay, you don't really find a bunch of free hydrogen ions floating around. What you see actually are hydronium ions. So in an acidic solution, really this is the key player, not hydrogen by itself, but hydrogen stuck to water. So when there's water around with lots of extra hydrogen, so the hydrogen comes from the acid, remember, water with extra hydrogen is hydronium. So you should associate hydronium with acid. Okay. Let's look at the other end of this, which is the bases. Okay, let's use one of the examples I said is a base but doesn't have OH. So one of those examples was ammonia. Ammonia is NH3. Remember, there's no OH here. So what happens is ammonia will take, remember, bases are things that are trying to suck up the hydrogens, take hydrogen out of the solution. So bases are trying to remove hydrogen from the solution by absorbing it. So what ammonia does is it takes one of the hydrogen ions. Remember that water is HOH. Water takes one of the hydrogens and sticks it to itself, and it becomes NH4 plus. Okay, so it's eaten up one of the hydrogens for itself, but it's taken hydrogen out of the solution. So what we're left with overall is water missing a hydrogen, hydroxide. Okay, so bases always contain hydroxide, which is what they knew for 40 years. They knew this, that hydroxide was present in basic solutions, but not because the bases donate the hydroxide directly, but because the bases take hydrogen away from water. And what's left over is actually hydroxide. So hydroxide is the leftover after water has lost a hydrogen, which is the opposite of when water is exposed to an acid. Water has an extra hydrogen, H3O. Okay, so you get the sense that water can really be an acid or a base. So in a normal sort of neutral solution, we see mostly water, H2O. In an acidic solution, there's extra hydrogen, so we get H3O plus hydronium. But in a solution with lots of base, we're missing hydrogen overall, and what's left is an OH, or hydroxide ion. So we can see all three of these in a solution. So I can kind of jot this off to the side. So OH we get when there's hydrogen missing, so that's hydroxide. And this is for basic solutions. Make this wider. H2O is regular water, which we knew. But then if I put one more hydrogen on there, so water with an extra hydrogen, that's H3O, actually H3O plus. That's hydronium. And this is always present in acidic solutions. Okay, so water that is exposed to acid gets this extra hydrogen, and water that's exposed to base loses a hydrogen to become OH minus. Okay, so I hope that was a good introduction to acids and bases. I'm going to have a quick follow-up questionnaire that I'm going to have you guys do.